All right, so now let me talk about the Riemannian metric, um, distance and gradients. And let me sort of just recall that, what we're trying to do is to develop the necessary differential geometric setting to be able to talk about various types of optimization algorithms on manifolds, okay? Um, and what we've done so far is to talk about the notion of tangent vectors and, it's like differentials of maps. And one of the things we observed was that tangent vectors can be identified in some way with the notion of directional derivatives. Okay, so the next piece, which is missing, if you will, with a view towards developing things like gradients, is that it's not just necessary for you to know how the function changes in a particular direction. You have to have some way of, if you will, measuring the length of the vector, because for example, when you have it's like when you have a gradient descent algorithm optimization, you want to have that the function changes the most, basically, for a direction, but the direction has to be somehow normalized, if you will. Okay, so you have to again be able to measure lengths of vectors in essence. Okay, so anyway, so you have that tangent vectors on manifolds, sort of generalize the notion of a directional derivative. Okay, so in order to determine which direction of motion results in a steepest increase in some cost function, in f, right, we need to have a notion of length. Of tangent vectors, right? Okay, so the way this is done, as you might expect, is that, well, it's like the tangent spaces are linear spaces. So in a linear space, the usual way we measure the length of a vector is through an inner product or norm. Okay, right? So we can do this. Well, okay, I mean, it's like, yeah, usually it's like, well, you measure the length, it's like through a norm, but it's oftentimes desirable to have that norm, it's like being induced by an inner product. Okay, so we will sort of endow each tangent space Tx of m, right, with an inner product. Okay, which has this sort of bracket notation, and the sub x here is to denote the fact that this inner product could depend, it's like on the base point x. Okay, so this is a bilinear symmetric positive definite. Form. Okay, and of course it's like what usually happens is that given that inner product, it induces a norm. Okay, so the inner product induces a norm. So the norm of a vector x, right, is defined to be the square root of the inner product of the vector with itself. Okay, and this norm is defined on Txm. And then oftentimes we omit the x. It's like if there's no risk of confusion, then so with that, then we can talk about the sort of direction of steepest ascent, right? So the normalized direction of steepest ascent, right, is just the following. It's the tangent vector to a point in the manifold with the property that the norm of that tangent vector is 1, and you want to look at the arc maximizer of the directional derivative of f in the direction. Okay. So you look at all possible unit vectors. It's like based at a point, and it's like you try to find and maximize this directional derivative. Okay, so that's sort of consistent with what we know. All right, so if you smoothly assign this inner product on each tangent space, right, then you endow it's like the manifold with what is called a Riemannian structure. So it makes it what is known as a Riemannian manifold. So a manifold with a smoothly varying inner product is called a Riemannian manifold. And then this smoothly varying inner product is called a Riemannian metric. Okay, and then there's various notations. It's like one used for the Riemannian metric, right? So this metric is sort of denoted sort of interchangeably by a bunch of different notations. We've already seen one possible one, which is this sort of bracket notation. Okay, but sometimes it's denoted by a sort of G, right? G with two vectors. Sometimes G sub x. It's like to emphasize the fact that, again, it depends on x. Okay, sometimes just by this sort of bracket notation. And sometimes the bracket notation, but again, emphasizing that it depends on x. Okay. So, all right. So then it's like this Riemannian manifold. So the Riemannian manifold is a pair, right? It's a pair, let's say M, the manifold M, with the metric G. Okay. Where obviously M is a manifold. G is a Riemannian metric. On M. Okay. But in practice, of course, what oftentimes happens is that we just refer to the Riemannian manifold by M. It's like, and then implicitly assume that there's a Riemannian metric which comes along with it. Okay. So then it should be observed that any second countable Hausdorff manifold emits a Riemannian structure. So any second countable Hausdorff manifold. This is sometimes redundant because oftentimes when we refer to manifold, we sort of assume that it has the property that's second countable in Hausdorff. But there are different conventions about the manifold aspect. So just to be clear, it's like if you have a second countable Hausdorff manifold, right, then you have it emits a Riemannian structure. Okay. All right. So let's see what happens. It's like on a chart. Okay. And on a chart, then essentially what happens is that it allows you to represent this Riemannian metric in terms of a matrix, basically. Okay. So let's say you have U phi be a chart on a Riemannian manifold. Mg. And if you recall, if you have a chart, then there's a natural choice of basis with a tangent space, which is induced by that chart. And let me just remind you pictorially what I mean by that. So say you have a domain, right, U, and then this is a map to Rn, right? And then you have these level sets, constant sort of constant coordinate level sets. It's like in Rn, you can pull that back to the manifold, right? And then you can look at the tangent vectors. It's like to these coordinate lines, okay? And the claim is that those tangent vectors to the coordinate lines are going to span the tangent space that's on the manifold M, right? So there are various ways of denoting that. It's like, the same way that there are sort of basis vectors, it's like an Rn, it's like coming from looking at directions which correspond to, one of the coordinates being constant, right? Yeah, I mean, it's like all but one of the coordinates being constant. Let me rephrase that, right? Then, it's like you can do the same thing here. It's like because of this pullback of these, coordinate lines, it's like to the manifold. Okay, anyway. So let's see what happens. All right, so the components, if you will, of this metric, Riemannian metric G in the chart is given by just how it acts on the basis vectors, right? So I say Gij is defined to be G evaluated on Ei Ej, right? Where Ei is the ith coordinate vector field. Okay, and again, it's like these coordinate vector fields are these things which are tangent to these coordinate lines, which I talked about before. Okay. All right. So, and And the reason why that is sufficient, obviously, is because you've assumed that G is an inner product, which means that it's bilinear. Okay, so so knowing these coefficients of the components, it's like of the metric, is sufficient because you have any two vectors can be obtained as this in terms of the expansion into the basis elements. Let's put J here just to be certain, right? So G of these, the inner product of these two vectors, right, is equal to the inner product of this expansion but by linearity, you have that this is the sum and of course this is just Gij, right? So this is just the sum over I and J Okay, so again, the point is that if you know the metric components, if you will, right, and you know the coefficients, it's like for the expansion of each vector into this into this sort of basis, it's like of coordinate vector fields, right? Then you can take the inner product of any two vectors. It's like by knowing the components, it's like of the vector, it's like and the components of the metric. Okay, so so that's good. And then these things are just real valued functions on the domain of definition of the chart. Okay, so what sometimes happens is that you also think of these things in the coordinate chart itself, right? And then we refer to them by the same thing. It's like by sort of an abuse of notation. And then it's a question of context to tell you when you're referring to the, it's like the manifold versus the coordinate space. Okay. So one can also define real valued functions Gij composed with the inverse of the chart on the image of U, right? And we use the same notation. So this is contained in R, well, I had Rn here, but I guess let's call it Rd. Same notation for both. And then you can have, you can also think of it as a matrix valued thing, right? We can also have a matrix valued function. Let's call that G, which is a map from x hat to G at x hat. And x hat is like the coordinate representation, it's like of x, right? And as you might expect, G x hat, right, is a matrix whose I(j) component is just Gij at x hat. Okay. So again, let's draw a picture here. You have point x, right? You have the coordinate chart. You have point x hat, which is the image of this. And you can, given a abstract vector, it's like you can identify it with a sort of corresponding representative vector in coordinates, right? So the hat denotes the coordinate representative. So you could have c hat x hat, right, to be the linearization of the chart, right, applied to this point here, right? Okay, acting on the vector. Okay, the same thing is true for the other vector. Okay, and where, of course, x hat is the image of the point x, it's like by the coordinate chart. Okay, so these are just representatives of the vectors on the chart. Right, so all that makes sense, right? You know, because we had abstractly talked about the derivative of a map, it's like, you know, between two abstract manifolds, it's like, but if one of them happens to be Rn, it's like, then this gives you a sort of a nice realization of the vector in the coordinate chart. Okay, so, all right, so we have this matrix valued map, right? And then we have these representatives of the vectors, right? So we want to be able to say that the inner product. Okay, so we want to be able to say that G applied to C, and it's like, and the other vector is equal to this matrix. It's like acting on the two vectors in some sort of natural way. Okay, so so we have that G acting on these two vectors, right, is equal to so I'm just using the two different notations for now. Okay, but this is equal to one of the vectors transposed the hat, right? So this is the representative times G, big G x hat. So this is the matrix valued function which we talked about, and then the other function. Sorry, the other component representation of the vector. Okay. So this is in sort of in local coordinates, if you will. Okay. Okay, so that gives you some notion of measuring the length of a vector. So with that, it's like we can talk about lengths of curves, and then we can also talk about the gradient. Okay. So distance between points, if you will. Okay. All right. So the length of a curve. Gamma, which is a map from an interval, say from A to B, it's like 2m on a Riemannian manifold. M comma G, right, is defined by the following. All right, so L of gamma, which is the length, is just the integral from A to B of the length of this vector, if you will. Okay, so it's the square root of G of gamma dot T gamma dot T. Okay, so this is just, this is of course nothing more than the norm of gamma dot of t, right, which is induced by the inner product. Okay, so this gives you a length of a curve. It's like, and if you want to find the distance between 2 points, what you do is that you minimize over the length of all possible curves connecting those 2 points. So you have the length and then the Riemannian distance. On a connected Riemannian manifold. I should say path connected. Mg is just this distance map, which takes 2 points in the manifold and gives you a real number. And the distance between points x and y is the infimum over curves, where gamma is the set of curves of all curves in M, joining points x and y. Okay. All right. So that's fairly natural. Then if you assume that M is Hausdorff, which is sort of what we've been doing all along, then the Riemannian distance defines a metric. In the following sense, that first thing is that the distance between x and y is greater than or equal to 0, with distance between 2 points equal to 0 if and only if x is equal to y. Okay, so this is positive definiteness. Second one is the symmetry property, that the distance between x and y is equal to the distance between y and x. It's called symmetry. Third one is the triangle inequality, the distance between x and y plus the distance between y and z is less than equal, greater than equal to the distance between x and z. So there's triangle inequality. Okay, so you should be careful to distinguish between the Riemannian metric and this notion of a metric, right? So the remark is that a metric is an abstraction of distance, and a Riemannian metric is an abstraction of inner products. Okay. So, but of course, these two things are related because the Riemannian metric, as we've seen, defines a Riemannian distance, which is a metric. Okay, so Um, anyway, okay, so now we're in a position to talk about gradients. So if you have a smooth scalar valued function, f on a Riemannian manifold, M, the gradient of f at x, which is denoted by grad f at x, right, is defined to be the following. It's defined to be the unique element Tx of m, unique element of this tangent space of m at x that satisfies the property. So let me write down that equation up here. So it satisfies the property that the inner product of the gradient f of x with an arbitrary vector is equal to the sort of differential map of f at the point x in the direction of that vector. This has to be true for all vectors in the tangent space at x to m. Okay, so the coordinate representation of this vector is the following. So grad f coordinate version of it at the point x hat, so the hat represents the coordinate representation, right, is the inverse of the metric times the usual. So here I'm going to distinguish between the capital grad and the lowercase grad. So the capital grad is the usual notion of the gradient in vector calculus. So you can take the gradient of f hat at the point x hat, right? So this is just now a scalar valued function. It's like on the model space for your chart. Okay, so where G is the matrix valued function, and sort of this capital grad is the Euclidean gradient. On RD. So grad of f hat at x hat is equal to just the partial with respect to the first component of f hat x hat all the way up to the partial with respect to the thief component of f hat x hat. Okay, all right. So so again, the point is that once you endow the space with this inner product structure, the Riemannian metric, right, you have now the ability to talk about gradients as opposed to just directional derivatives. So the gradient of a function has the following steepest ascent properties. Okay. So the first one is that the direction of the gradient is the steepest ascent direction. So what I mean by that is that if you normalize the gradient by its length, that is equal to the arc maximizer of the directional derivative of f at x. It's like in the direction cos c, where cos c, where you sort of extremize over cos c in the tangent space with the property that cos c has unit norm, right? And then the second property is that the norm of grad f gives the steepest slope. Which is to say that the norm of the gradient is equal to df of x grad f of x divided by the norm of grad f of x. If you prefer, it's like what this is that it's the maximum over all tangent vectors with the property that the tangent vectors have unit norm of the directional derivative, right? Okay. Yeah. Okay, so then the point is that these two properties obviously are important when you're going to try to develop optimization algorithms and manifolds, right? So these are sort of the two main properties you'd like to work with. It's like, and then constructing, it's like a iterative scheme for doing optimization. Okay, so let me just stop here for now.